change percentage. No, the percentage. What was the percent change? You weren't able to find X? Well, because the practice test, are people still working on that problem? Because if I go through that, then it's not really a mock test, yet. So you want to go through it like it were a mock test,
Will you have time after class to show us the ones that are connected? Just so that we can understand.
Because I want to know how to do it because I can't really.
I also redid 15 and did the reset.
Um, (15) and 16. 15 worked. 16 didn't work.
I did 15 again with the reset and it still didn't work. It still failed.
15 you have to back up, plug out.
Huh?
You have to back up, plug out.
I did the reset and then plugged right in. I don't know, I just don't know what I'm doing.
Well, okay. The only situation is if I go through it, then it kind of kills the mock test aspect of it for other people. And since their homework problems kind of similar to it that you can find in the book, with the solutions guide worked out. But let's see. Well, let's see. What was the equation that you generated? The mathematical equation that you generated. This is for number 16
Yeah.
on the practice.
Yeah. I got 1.09 times 10 to the 5th equal to
1.09 times 10 to the 5th.
equal to, and the top is 0.100 minus 2x times 0.100 minus x, and then over 0.100 plus 2x squared. I think I'm missing.
Are you missing any
Yeah, I think I'm missing some
square terms or cube terms?
Okay, so for the 0.100 minus 2x, that one is squared.
Oh.
Yeah.
So if you look at this, there's always a fallback option. The fallback option is to do successive approximations. Did you try successive approximations on this? So this is the fallback method, because successive approximation should work. It just might take you a heck of a long time, that's all. And with these, like a cubic function, you might hit some kind of minimum. Well, so you could try that, or you could try some tricks. Did you try any tricks on this, Mimi?
I was doing the simplifying assumption.
You
But then I also reset it before too.
you also reset it?
Yeah.
When you did the simplifying assumption, you used the simplifying assumption on this?
Yeah.
Well, is this a reset K or the regular K?
Regular.
And how about you? What did you try?
We did reset first, and then we did simplifying.
Okay, why did you do the reset first? What was your strategy in doing the reset?
To get 0 moles on one side so that we can get less X's.
All right, but was there any other reason you reset it? What direction did you reset it? To the right or to the left?
To the right, because it's favoring products.
So you reset it to the right because it was favoring products?
And then so it was simpler to use with the simplified assumption. But
Okay.
then we did the percent change and it failed.
Okay. You did the percent change and it failed. And so is this the one with the reset or the one with no reset here? This is the one with no reset. And then you reset it.
Yeah.
All right, we could, you know what? Tomorrow, unfortunately, I have to cancel my office hours. So I'll go through it completely today. But usually for the mock exam, I want you guys to figure it out because, just like on a true exam, how do you know you have the right answer? And so you have to devise a strategy about how you check your answers. You know, a lot of people say, "Oh, how do you know you got the right?" I just look it up in the solutions guide or in the back of the book. But you know, there's a lot of problems you can't do that, and so you have to figure out how to check your answers as well, at least at the best you can. You know, as far as checking your answers go. And so the thing is, you know, what I'm trying to gauge is, you know, how much confidence do you have in your particular answer? You know, when you do a mock test like this, you know, do you have zero confidence in your answer that you need somebody to tell you the answer? Or do you go through it over and over again and you go, wow, I'm absolutely sure I did this right. You know, and I know I got the right answer, barring any, you know, some simple mistake. Well, that's the level you should try to, you know, get to, where you're saying to yourself, I'm doing this right. Everything's right. It's clicking. It should be the right answer. And so I'm fairly confident it is. The reason you have to do that is pretty soon, you know, a lot of, as you go on, you know, next year, the year after that, pretty soon there are no answers. And you have to figure it out, and you have to argue, you know, that according to your calculations or according to how you did this, you have the right answer, you know, that kind of stuff. Because to me, that was a shock, because I always thought somebody would have the answer, you know, as I progressed through my education. You know, somebody's got to know the answer. Then you hit this point where nobody knows the answer. I mean, you're the only person working on this particular field, you know, and you have to convince others that you got the right answer. Okay. And so this is just a start to it. You know, it's always nice to have the answer, obviously, so you can check, you know, that you're doing it right. But you know, there's a lot of value in learning about how to check your answers. So we'll go from this one from the beginning and take a look. What was the reaction? Number 16.
2 Fe, 2 plus aqueous. And then 2 Hg, 2 plus aqueous. That gives you 2 Fe, 3 plus aqueous, and Hg2, 2 plus aqueous.
What was the Kc again for this? I just erased it.
1.09 times 10 to the 5th.
Okay, immediately, do you see it? 10 to the 5th. Is that big, small? What is that? It's big, which means what? It means most of the atoms should be on the right side or the left side. Yeah, it should be all product. What are the initials that were given?
It's 0.100 molarity for all of them.
0.100 for all of them?
Yeah.
And so if we have 0.100 molar for all of it, then we know most of the atoms should be on the right side. You know, this is a pretty good candidate for resetting, so it's good that you reset it immediately, because that's going to save you math later on. And so, you know, automatically I would have reset this like you did. We would reset it to the right because of the big K, so we just reset. And so there's a lot of good, what do I mean by minus 2y? What I mean is, you know, we got to figure out what the limiting reagent is, you know, and so this is why I just put in the variable, minus 2y plus 2y plus y. Okay, then we look, if we're resetting, we're going to have 100% forward reaction, so what's the limiting reagent going forward? You can say there's no limiting reagent because this is a, what kind of reaction? Stoichiometric reaction. So it's perfect stoichiometry. That means this is going to go down to 0. We'll use all that. This is going to go down to 0. You know, completely consume the this. You know, sometimes we go backwards, and the same thing. When we're going backwards, we look for the limiting reagent. You know, if we reset this to left, which one's the limiting reagent here? If we reset this to left instead of the right, which one would be the limiting reagent? Not H2, Hg2. Hg2. Hg2, 2 plus, mercury 1 ion. If we reset this way, is Hg2 2 plus the limiting reagent? If we think, if I have 0.100, then I need twice as much iron. Do I have twice as much iron? No. It turns out that iron is the limiting reagent here. So if I reset this way, this would be the limiting reagent, so I consume all of it, which means I'm going to have some excess reagent left over. And so this would go down to 0. This would go to what? 0.05, right, half of it. And so we have 0.05, and then over here it would be 0.200 and 0.200 if I reset it to the left. But it makes no sense to reset this to the left because of what my K is telling me. Now, if the K is like around 1, 2, 3, 10, minus 1/10 or something like that, then it doesn't really matter which side you reset it. Because we expect more an even distribution of product and reactants, but still resetting helps because we get more zeros. If we get more zeros, we have fewer binomials we have to multiply out, which just saves time for math. Actually, how many people got this, number 16, the answer? Someone get the answer to this? Well, this is just pretty much a standard ICE problem from chapter 15. So you want to be able to get this. So I hesitate doing this. How many people tried this? Okay, just a few of you. See, if I go through the answer now, well, if you haven't tried it yet, then I guess I'll just go through it. Now, this is going to be 0.200. This is going to be 0.150. Is that right? Oh, that's what you got? All right. And so here, Kc is equal to the iron 3 plus squared times the mercury 1 divided by the iron 2 plus squared and the mercury 2 squared. It's actually fourth order. The earlier K expression was wrong. Double check that. Or was it squared on the bottom?
Yeah.
Oh, it's fourth order? All right. So what do we have here? Well, that's our initial. So the change is going to be easy now that we reset it. Change should go plus 2x molar, plus 2x molar, minus 2x molar, to minus x molar. And so at equilibrium, I expect 2x molar, 2x molar, 0.200 minus 2x molar, 0.150 minus x molar. And so the iron 3 here is 0.200 minus 2x squared, 0.150 minus x divided by 2x squared, 2x squared. This we could simplify a little bit. 0.200 minus 2x squared, 0.150 minus x over 4 times 4 would be 16x to the 4th. So then you guys tried the simplifying assumption?
Yeah.
Okay, let's try. What did you say as your simplifying assumption? That 2x is smaller than 0.2 or x is smaller than 0.15? Yeah, good. 2x is smaller than 0.2, which gives us 0.200 squared times 0.150 divided by 16x to the 4th. Now this is easy to solve for x. What did you get for x?
That 0.007.
0.0076 5. 3 zeros, okay, 00007 6 5 8. We're allowed 3 sig figs here. Yeah, 3 sig figs, so let's carry one extra. All right, so let's determine the percent change. The percent change is going to be 2 times that. 2x over the initial 0.2 times 100%. I'm going to ignore sig figs here because and so what did the percent change come out to?
0.65%.
Oh, okay. So this failed. And so one option is, you know, it depends. If you ran out of time, you just use this value for x and then calculate the equilibrium concentration. Say it's going to be off. It's going to be off because this is pushing. The simplifying assumption is not really so valid when the change is so big. You know, when the change is small, like we saw like yesterday, like 10 to the minus 10% or something like that, 10 to the minus 9%, then no problem. Simplifying assumption works wonderfully. So, unfortunately, this doesn't work, this SA. Uh-huh.
So when you did the simplifying assumption, you chose the smallest initial, and why is it 0.2 instead of 0.150?
Because of this. You want to normalize it. What I mean by normalize is you want to normalize the change. So the change here is 2x. To normalize it, we multiply this one by 2. And so if this were 2x, then we'd have to double this one, which would be 0.3. And so this would be 0.3 minus 2x, which is the same, I mean, in terms of percent change as, and so which one is a bigger change? It would be 0.2 versus 2x versus 0.3 versus 2x. So that's why we just picked this one. So you guys were right in selecting that one.
Oh, and also for the mercury 2 plus,
Mm-hmm.
for the initial, how did you get the 0.150 molarity again?
Oh, because we figured out what y is. What is y? Here. So 0.100 minus 2y is equal to 0. Therefore, y is, well, 2y is 0.100, and y is half of that. Half of 0.100 would be 0.050. And so this would be 0.100, this would be 0.100, this would be 0.050. So 0.100 plus 0.050 gives us 0.150. That's where we got it from. All right, what's next for us to try? Well, we ran out of tricks, right? We did the reset. We did the simplifying assumption. And so the only thing left to do is successive approximation. Now you might think, oh, well, this was a complete waste of time. It wasn't a waste of time. Because if you have a close guess, initial guess, then you're going to save yourself some time. And so what would be a close initial guess that we would guess for x, doing successive approximations? We use this. You know, even though this was wrong or off, it's still kind of close, you know? So our first guess wouldn't be this many digits, though. Usually we try to do a first guess as 1 digit. And so what would you call that? I would try 0.00008. I'd go for 0.00008. I think that semester, last semester, I gave that test. I think the fewest number of guesses it took somebody was like about 4 or 5 guesses. They guessed it in 4 or 5 guesses. The longest was maybe about 30 plus, and they didn't get the answer. They gave up after 30 guesses. But anyway, we'll just try and see how many guesses we can get it. I don't remember the answer, so we'll just try. You tell me. The first guess, 0.0008. Plug that in, you know, this would be 0.0016, so minus 0.2 minus that would be, 0.184 squared. It's a bit of a pain, but you guys know, like, calculator order of operations. You should be able to do it quickly, right, on your calculator. Actually, I have a calculator in here. That's right. I'm gonna do it. Sure. I have the TI-30. I don't understand why everybody recommends this. You know, I went to Target to look for TI-30XA. They're selling, the normal price for this is $20, and then it was on sale there at $14.99. I was thinking, my gosh, you know, compared to the features. Then I looked on Amazon, it was like $10. Bought one on Amazon. I needed a TI-30 for something. Usually when you use the calculator, this always, if you don't, when you use the calculator, does the calculator care about these zeros? No, but you know, a lot of people, they want to be proper and they want to put in the zeros where it makes no difference if you put those zeros or not, including this zero.
We add added a zero, so it should be 0, 0.
It should be double zero?
Yeah.
All right.
It should be 0.00.
All right. Let's just do, okay. There's the one too many zeros, so 0.00758 or whatever it was. All right, so our first guess is going to be 0.008, which is going to give me 0.016. So 0.2 minus 0.016 equals squared times parentheses 0.15 minus 0.008, close parentheses, divided by 16, divided by 0.008 to the fourth. Let's see, 0.008 to the fourth equals 7.3 times 10 to the 7.3 times 10 to the 4th. I don't want it in 10 to the 4th, so I'm going to make it 10 to the 5th. I'm going to call it 0.733 times 10 to the 5th. So we're a little low, right? And so should we make x bigger or smaller? Smaller, bigger, smaller. Well, it's, I got 3 smaller, so let's go smaller. 0.007. And so let's try it here. It's going to be 0.2 minus 0.014 equals square that times parentheses. That's going to be 0.143. So I don't need parentheses really. Divided by 16, divided by 0.007 to the 4th. So we went smaller in 2, 4, 5. I got 1.2. 1.28. 1.28 times 10 to the 5th. We're a little bit too big now. So where should we go next for our next guess? 0.075? Okay, let's try that. 7.2?
Yeah.
All right. Let's do that. 0072. So this is the way I'm going to do it. I'm just going to do 0.072 since I don't want to do any calculations in my head. Times 2 minus 0.2 equals square that times parentheses 0.15 minus 0.0072 close parentheses divided by, oops, I miskeyed it. Let's start over again. If somebody gets the answer, let me know.
Isn't it 1.14 times 10 to the fifth?
Yeah, I got that too. 1.14 times 10 to the fifth. Is everybody getting these same answers? Okay, let's continue the table up here. X. We're very close now, aren't we? Very, very close. So what's the next guess?
0.0074.
Okay, let's try it then. 0.0071. Let's go for that. Right, 2 times 0.0071 minus 0.2 square times parentheses 0.15 minus 0.0071 close parentheses divided by 16 divided by 0.0071 to the fourth. I got 1.2. 1.21 times 10 to the fifth. So I look at that, you know, it makes sense because it's between 70 and 72, so we should be between 1.28 and 1.14. We probably should have went which way? We probably should have went, yeah, bigger to what? Yeah, 0.0073. But it's no big deal, you know. Eventually you'll get the right answer. It doesn't matter if you take 30 guesses or 40 guesses. You know, the thing to do is not to give up. And just persevere through it. 2 times point. This is, you know, this is a lot of calculator work, but it's not heavily weighing on your mind. You know, it shouldn't be. It should be mentally straightforward. .079 times 10 to the fifth. That's like 1.08. We're very close, aren't we? What do you want to do next? You know, we're a little bit too small. This is too big. 72 was too big. 72 was 1.14. 73 is too small. But what is it closer to? This is 1.08. That's 1.09. So it's very close to. So what do you want to do for your next guess?
Somewhere in the middle.
Not in the middle. I would go closer to 3. So give me a number closer to 3. 7.4 is going to go way too. Yeah. 7.4. Do you see the trend? 72 to 73. 74 would get even smaller, taking us farther away. 729, that sounds good. Like 00729. So let's try that. 0.00729. And you know, right, this is taking us a long time, right? This is taking us a long time because I'm taking my time. On a test, I wouldn't be taking so much time. I'd just go ahead and try, right? And so it actually goes a lot faster on the test. If you're, don't use this as a gauge to how long it takes, because this is a very relaxed pace. I'm sure you could key it in much faster. I mean, or at least, without less discussion. 729 times 2 minus 0.2 squared divided by, I don't want to do, I'll just do divided by 16 times 0.15. Oops. But you need practice with your calculator, about what the most efficient way to key in things. A lot of people will do like, they'll do a lot of unnecessary operations. And so somebody will key it in like in 3 keys. Another person will take like 5 to 10 keys, key in the exact same equation. So we got 1.085 times 10 to the 5th, which rounds to, we're done. How many guesses? We did it in 6 guesses. Pretty good, huh? So still, we didn't beat the other guy's record. It was like 4 or 5 guesses. I can't remember exactly, but it was very few guesses. I was surprised. I thought he cheated, because how could he guess it in 4 or 5 guesses? I mean, But we got it in 6, so that's all right. So we aren't quite done yet. We need to get this to round to that. Well, it rounds to that, and so we're done, basically. And so this is our x, 0.00729. And so we will put that in over here, 0.00729 times 2. .01458 molar. This will be the same 0.01458 molar. And then 0.2 minus 2x. So 0.01458 minus 0.2, it gives us 0.185 or 18542 molar. 0.150 minus x. So 0.15 minus 0.00729 is 0.14271 molar. All right, what should we do next? We should check K. These equilibrium concentrations should give us this ratio. So we'll take the iron 3 concentration. Well, the iron 3 concentration is this, and we need to square it. So let's go ahead and take that. I'm going to carry all the digits to try to avoid round-off error. And so 0.18542 squared. And then we look for the mercury 2 plus concentration. Wait a minute. Don't I need to double this? Do I need to double this? What? Do I need to double this because it's 2x, right? No, I don't double. X is just some number, and this was 2. This is the actual concentration. I don't have to double it. It's not, it's just whatever that concentration is times this, 0.14. Actually, now I lost track. 0.14271. Divided by, okay, these are both the same concentration, and it's going to be raised to the 4th. So I'm just going to do divided by 0.0 1, 4, 5, 8 to the 4. And what do I get? I get my K value comes out to 1.085 times 10 to the 9. 1.085 is pretty much, I mean, if you wanted, you know, there are people who want to get it right on. And so some people did more guesses and they got it right on. They got it 1.090. You know, and they kept guessing because they wanted it right on, which is great. You know, if you want to do that, you're welcome to do that. But this is what the minimum I'd require. The minimum I'd require would be just to make sure it rounds to the proper number. Okay.
Wait, Professor, how come you didn't square the iron 3 plus, but for the bottom you squared those two concentrations?
I did square the iron 3 plus.
Oh, you just said don't do it. You said
No, I said double. Do you double it?
Oh.
Double it meaning this. There's a 2 here. Should I double it?
Double as in to check the K? Or
No, is this the correct concentration or do I need to double it because there's a 2 here?
no?
Some people actually double, you know, I don't know why, but some people actually double this because there's a 2 here and they double this one. I don't want to confuse you. If that sounds weird, it is weird. I mean, it's weird because it's like saying this. Can I put 1 gram of hydrogen in 2 grams of oxygen? Is that allowed or forbidden? If I mix this mixture together and then try to ignite it, is that allowed or forbidden? It's allowed. You can mix these in any ratio you want. That's what a mixture is, right? A mixture is, but some people think it has to be a 2 to 1. That carries over into this, but forget it because I just see that once in a while that somebody does that. And so let's not. So it came out good, and so we're done.
I got to the 5th power instead of the 9th power.
Oops, to the 5th power is what it was supposed to be. If it was to the 9th power, we'd be way off, right? Way off. This is to the 5th power. I just accidentally wrote it to the 9th. I was thinking about something else. Okay, any questions about this? Any other questions about this? So this one is where we had to pull out all the tricks and like the other, we did one like this, just like this in class.
I have one more question.
All right,
It's on number 10, the multiple choice one.
all right.
They're asking the deviations from ideal behavior are more significant for aqueous iron 3 plus than iron 2 plus, true or false. For this one, this is where we talk about like the charge, whichever one is higher, kind of thing, because it pulls more, the charge is higher.
Yeah, that one talks about, you know, there are 2 things that cause deviations from ideal behavior. Have you heard of ideal solutions? You've heard of ideal gases, right? Ideal gases versus real gases. What's the difference? Well, ideal gases, there's no intermolecular attractions. The volume of the particles is 0, right? Well, the exact same concept can be kind of applied to solutions. We have ideal solutions and real solutions, and solutions start to deviate from ideal. Ideal is your stoichiometric concentration. And looking at the table, there are 2 things that cause the deviations from ideal behavior. What are they? Well, Mimi mentioned one, the charge. What's the other one? This is the page, the one page I asked you to go back and read from chapter 13. The same thing happened last semester. Nobody went back and read it, actually. The interionic attractions, exactly. Interionic attractions. it's being busy students, you always got to weigh things. Is it worth reading for maybe one question or maybe two questions, or just skip it? You know? So I'll let you judge. Not that I'm going to ask you. I didn't really emphasize it. Last semester I tried to emphasize it. I spent actually more time going back and reviewing that. And activities, and that kind of stuff. All right, what was the other question you guys had? 15?
Yeah, 15.
What was 15, the problem with that?
We kind of had the same problem that we just simplify an assumption and we didn't get it failed again, so we probably have to do
It failed the simplifying assumption?
So we did reset after that, and then I used plug that to solve for X, but I did the justification rule and it still failed. It was all like
It failed.
Then you have to do it again successfully.
All right, let's take a look at 15 then. Well, does anybody know the other factor? Charge is one of the factors that causes deviations from ideal behavior. The other one is, that was in the table data, the NaCl versus the MgCl2 versus the PbNO3/2. I know those because I've looked at that table like hundreds of times. I've looked at the numbers. Actually, I remember a lot of the numbers actually on the table because just seen it. My memory is the worst, but you know, when you see something so many times over and over again, it tends to stick, you know. But my memory is, especially with, I have a hard time with names, fortunately. The other factor, well, it was, nobody remembers at all? Just take a guess. Hmm? Well, it's not amounts, but it's sort of like that. We don't call it amounts though, because if you have a large amount of milk versus a small amount of milk, you know, it's still milk. Concentration, right? Right. It's like if you have a gallon of vinegar versus a quart of vinegar, still vinegar, right? But if you have a quart of concentrated sulfuric acid versus a quart of dilute sulfuric acid, is it still sulfuric acid? Yeah, but it can behave a lot differently. And they have a lot different activity. This concentration was the other factor. These types of things on tests are what I used to think of as give me points, you know? Anything that was covered in class or anything that was in the homework or in the assigned reading, those were give me points. I'm always grateful for those points because, you know, if you prepared well, you should be able to get those 100%, right? The other questions were not give me points. Some questions are just out there, you know. I tend to focus on things that I talk about in class and tests, as you can see from that mock exam, the last semester's exam. But number 15, what was that, the reaction?
It was CO gas plus CH2O gas goes to CH4 gas plus water gas. Kc is 190. Their initial concentration
I must have given you at least 3 sig figs, right?
It was 1.00, yeah.
Hydrogen gas.
How about the CH4
Zero.
and H2O?
Zero.
So H2O is a gas here. If it were liquid, I would exclude it from the ice table.
Professor, is hydrogen gas, not water gas. For
Oh,
the
okay. Hydrogen gas, thanks.
It's for the reactants, not the product.
Oh, this is a redox reaction then. In this redox reaction, we're reducing carbon monoxide using hydrogen to methane. Water. This is one of the ways of thinking about making methane, but you know, hydrogen's not so easy to make sometimes.
Oh, there's also a 3 in front of the hydrogen.
Oh yeah, it's not balanced, is it? That's 6, and that would be 6. Yeah. Oh, look at what I did here. 1, 3. I made it stoichiometric. Made it stoichiometric. But you know, I don't like this particular problem because of the K. What's the K? It's 1.9, which tells me what?
Equal amounts of the
Yeah, and so resetting in this case and the simplifying assumption, well, resetting's fine, but it's not really required here. And the simplifying assumption is likely not to work, right? Because there's going to be a significant change.
I think Casey is
Casey
190.
is 190, it's not 1.1.
Oh, 190, 190. Okay. Well, maybe that's a little bit better, but still not great. Because it's still, you know, when you see a very large or very small K, then the simplifying assumption is likely to work as long as you reset it. But when you have a K like this, the simplifying assumption, it's probably not going to work like you guys found out. Probably not going to work. And so here, what do we do for this particular one?
We find Q.
We don't need to find Q because we know it's got to go in the direction of the zeros, so it's not necessary. We might as well reset it. Reset it. So it turns out that this is going to be minus y minus 3y plus y plus y. And so initial here would be, well, this is stoichiometric, right? And so this is going to go to 0, 0, and 1.00 molar and 1.00 molar. And so the change here is going to be plus x molar plus 3x molar minus x molar minus x molar. And so at equilibrium, I'm going to have x molar, 3x molar, 1.00 minus x molar, and 1.00 minus x molar. Then Kc, this is concentration, so it's going to be methane concentration times the H2O gas concentration divided by the CO. I'll emphasize H2O because, you know, we handle H2O differently, again, whether it's a gas or a liquid. If it's a gas, then it participates. If it's a liquid, it doesn't participate. So this is going to be CO, and then the H2 cubed. And so on the top, I'm going to just simplify it right off. We're going to get 1.00 minus x squared divided by x times 3x to the third power. Okay, doing some further simplification, this is going to be 1.00 minus x squared over 3 cubed is what, 27? X to the fourth. X to the fourth. Yeah. Okay. I told you some of the tricks that I use, right? But there's some tricks that you learn in just algebra, you know, in simplifying things and other things. You know, when I look at this particular equation, boy, this looks horrendous because it's fourth order. Horrendous. And well, one of the tricks I would try is the simplifying assumption. So let's go ahead and try that, the SA. And so if I use the SA, x is going to be smaller than 1, which means this is going to go to 1 squared, and 27x to the 4, which means x comes out to what? 0.118. If this are 100, this is going to be an 11.8% change. Oh, too big. So failed. So we reset, we did the simplifying assumption, it failed, that means we have to fall back on successive approximations, but man, this is exhausting because that's 2 successive approximations in a row, right? But in this particular problem, there's a trick I haven't talked about because this is a trick you learn in algebra, and this is a trick you should use to solve this particular problem. The trick you learn in algebra is to square root of both sides. If we square root both sides of this, right, then we're going to convert it from a fourth order equation to a quadratic, and then we'll just use the quadratic solver to solve it. Okay. And so that's something that last semester, some people, actually last semester, a lot of people did successive approximations to solve this, which is fine. You could do it, you know. Or you could just use the quadratic for this. And a lot of people had the quadratic calculator, so they were able to do it without too much trouble. It's still a pain, you know. Quadratic is still a pain. We've got to get it in the quadratic form. Okay. All right. What other questions do you have? Because unfortunately I'm going to cancel it. Like I said, office hours tomorrow, because I have to take care of some stuff. So we can spend some time today going through problems if you want.
Okay, so for 13, the question is 10 gallons of 6 molar H plus has twice the activity as 5 gallons of the same, true or false? And then we were talking about the ideal behavior of the charge and the concentration. But since the concentration is the same, it would be false because...
Right.
Because if it was different concentration, then that would be true.
That would be true. Right. It depends on the concentration. The activity is going to depend on the concentration. If the concentration is the same, the activity is the same. The amount of reaction is going to be different, you know, but the activity will be the same. That is, you know, it's like a battery. You know, I have a D cell battery, which is like twice as big as a C cell. So does a D cell have twice the voltage of a C cell battery if it's twice as big? No, it's the same voltage because it's made up of the same chemicals. So if it's the same voltage, then what's the difference between a C cell and a D cell? A D cell just has a lot more, and so it lasts longer. You know, that's all. Okay. We'll look at batteries later, actually. All right, other questions on that? No? Good? All right, I'm not going to talk anymore. We'll just go straight into lab then today. Again, I know a number of you have started your unknown. So once you start your unknown, the lab manual has to be closed, right? It's all lab notebook. And you're not allowed to talk to anybody. But let me forewarn you. The procedure, is the procedure for the known and the procedure for the unknown going to be the same? Not at all. Not at all. There are people And this happens every semester. There are people who want to do the exact same procedure, but you can't. It's not going to work. You have to modify the procedure to make it work for your unknown. Okay? And how you modify that, well, you got to figure it out. You know, some branches are going to be missing. You can't do certain things, right? Because you don't have all the iron. And so, you know, even before you start your unknown, you want to give it some thought, you know, because once you start your unknown, you can't ask me any questions. But before you start the unknown, you can ask me, you know. Okay. All right, that's it.